30 miles under the ocean. One attempt, no second chance. If the machine stops, if the lining cracks, if the water finds the joint, that is it. The passage floods, the economies it was meant to connect absorb the loss, and the geological record simply notes another failed bore. We have done this. We have succeeded. And the reason we succeeded is not luck or bravado. It is a methodology, a way of designing systems that remain coherent while the ground beneath them keeps changing the rules. That methodology is what we are going to walk through, step by step, exactly as the engineers walked through it. What the ground contains, what forces that ground generates, how you build a machine capable of surviving those forces in complete darkness, and what decisions a crew makes when the rock stops matching the model. We begin by asking what actually collapses if the tunnel fails. Two national economies rest on a single fixed link. A breach does not merely delay traffic. It severs the daily movement of goods, capital, and people that each side has built its budgets around. Once seawater enters the bored tube, the damage is not reversible by pumps or patches. Politically, the rupture becomes permanent as well. Trust between the two governments erodes the moment one side must explain why its infrastructure now lies underwater and unusable. We therefore plan every meter as though the next decision must hold for centuries, because the cost of being wrong is measured not in budget overruns, but in the sudden, irreversible separation of economies that had grown dependent on each other's continuity. That framing changes what engineering means on a project like this. It is no longer a process of applying known solutions to defined problems. It becomes a process of designing for uncertainty, building systems that can absorb what we did not predict without losing structural coherence. Every chapter that follows answers exactly one question, and each answer unlocks the next. What does the ground contain? What forces must the machine survive? How do we design something that can act and correct itself in total darkness? And what do we do when the rock stops matching the model? Consider what the ground beneath the English Channel actually is. Not a single substance, not a stable, predictable medium that holds its character for miles. It is a stack of geological chapters, written over tens of millions of years. And those chapters do not announce themselves at the surface. Chalk gives way to stiff clay. Clay gives way to fissured limestone. Limestone gives way to water-bearing sand. And then, within a few meters, back to chalk again. No warning. No visible seam from above. The transitions are abrupt, discontinuous, and sometimes invisible even to instruments. Subsea tunneling differs from almost every overland project we have ever attempted. On land, a geologist can walk the road. They can read the hillside, sample the outcrops, drill test cores at regular intervals. The surface speaks. Here, the surface is silent. It is covered by 80 meters of seawater and another layer of sediment that tells you nothing useful about what lies below. So the engineers faced a problem that is not merely technical. It is epistemological. They needed to build a machine capable of cutting through ground they could not fully characterize in advance. If you cannot drill a test core every meter of a 50-kilometer route, how do you know what the machine will hit next? The answer shaped the entire design, and it begins with what we chose to measure and when. Marine seismic reflection surveys sent sound pulses through the water column and into the rock below. The returning echoes produced layered maps of density changes across the entire alignment. Then came borehole cores, spaced at intervals that still left most of the route untested between them. Together, the seismic surveys and the borehole cores let us construct a probabilistic model rather than a single certain picture. Zones remained where the reflections were ambiguous and the cores had never reached. We marked those intervals as unknown, carried the uncertainty forward as a design parameter, not as a gap to be filled later, but as a condition the machine itself had to be built to accommodate. The machine that followed was therefore sized and shielded for every plausible variation the model could not rule out. At a certain depth, pressure stops being background noise and becomes the central fact of the entire project. That threshold is not arbitrary. It is the moment when the water column above a point in the rock generates a pore pressure large enough to govern every material choice we make. Concrete mix ratios, steel grades, gasket tolerances, even the torque limits on bolted joints. The physics are direct. For every 10 meters of water depth, pore pressure in the saturated rock increases by roughly 1 atmosphere. At 60 meters below the seabed surface, the fluid trapped between rock grains is pushing outward with a force that would collapse an unlined cavity in seconds. The tunnel lining does not simply hold back that water. It must permanently resist what engineers call effective stress, the load remaining once pore pressure is subtracted from the total stress the rock exerts. That distinction matters more than it first appears. A lining sized only for water pressure fails when rock transmits overburden load. A lining sized only for overburden leaks, where pore pressure finds any joint or hairline crack. Every component must be sized for the sum of those forces, not either one alone. And what makes this genuinely unsettling is that the sum changes continuously along the alignment as the seabed profile rises and falls, and as rock permeability shifts between formations. We are not solving for one pressure. We are solving for a continuous function of pressure, and the lining must satisfy it everywhere, simultaneously, for the full design life. Here the engineering stops resembling construction and starts resembling experiment design. What do you change about a machine when the ground ahead of it has never been fully mapped? We did not select a tunnel boring machine from a catalog. We commissioned a hypothesis. The geotechnical surveys gave us probability distributions, not certainties. Zones where limestone would likely grade into fractured marl, where permeability would likely increase, where overburden pressure would likely reach values we had calculated, but never directly measured at that depth. The machine had to respond to each of those conditions in real time, because stopping underground to reconfigure is not a realistic option. The answer was variable density technology, a design that lets a single machine shift between open excavation and pressurized modes without surfacing. In practice, this means a single machine capable of operating in open face mode when the ground is stable and cohesive, and switching to pressurized slurry mode when it is not. Without surfacing, without disassembly, without interrupting the advance. The slurry, a dense bentonite suspension, is pumped against the excavation face to balance the exact pore pressure and earth pressure acting at that moment. In that formation, the machine is not drilling through a known medium. It is continuously interrogating an unknown one, adjusting its own internal state to match what it finds. That is not construction at all. It is a live experiment with consequences measured in human lives. But the machine's ability to correct itself is only half the problem. Because the machine's ability to correct itself is only half the problem. The other half is knowing where the machine actually is. 2 machines, 2 launch shafts, 30 miles of solid geology between them. Each boring machine begins cutting from its own end, advancing blind towards something it cannot see, cannot hear, and cannot touch. The question is not whether they will meet. The question is whether they will meet at the same point. The answer lives in mathematics and light. Every TBM carries a laser gyroscope that measures rotational orientation precisely enough to detect drift of fractions of a degree over hundreds of meters. Above ground, A GPS control network continuously monitors reference stations at each portal, feeding real-time positional corrections into the guidance model. The two datasets are reconciled constantly. If one machine begins to wander, the correction is calculated before the error compounds. Because errors do compound, a deviation of a single degree, left uncorrected across 15 kilometers, produces a miss of more than 250 meters. The geometry is unforgiving. So, engineers specify what they call the breakthrough tolerance, the maximum allowable horizontal and vertical offset at the moment the two machines finally break through to each other. For most modern undersea tunnels, that figure sits within a few centimeters. Over tens of kilometers of rock, through changing densities and unmapped voids, two machines guided by light and mathematics are expected to meet within the width of your hand. And the lining they leave behind as they advance is not a passive shell. It is a prediction made physical. Each ring is assembled from bolted precast concrete segments whose joints carry compression gaskets machined to tolerances below a millimeter. Before a single ring leaves the factory, we run load models that incorporate asymmetric ground pressures, long-term creep, and possible fault movement across a design life of a century and more. Those models dictate segment thickness, bolt patterns, and gasket geometry. We test at full scale. Only after the data confirm that the assembled ring will stay watertight under the worst credible combination of loads do we authorize production. The lining becomes both structure and ongoing verification, its measured performance held against the same models that shaped it. Then the ground changed. We had aligned every parameter to the model the surveys supplied, advancing the cutter head under steady pressure and torque, reading the telemetry, watching the margins hold. Then the face opened into an unmapped water-bearing fault. Flow surged against the shield. Sensors registered an immediate spike. The model that had guided us meter by meter ceased to match the rock in front of us. We stopped the drive. We recalculated face pressure and advance rate, while the segment erector already held the next ring in position. And we revised the experiment in real time. When the hypothesis fails underground, we do not retreat. We intervene in the geology itself. The first correction is permeation grouting. Lances are driven ahead of the stalled cutter head, and stabilizing compounds are pumped into the faulted rock, filling fractures and binding loose material until the face regains enough cohesion to support the original face pressure. Where water inflow persists, we may shift to compressed air within the working chamber, raising internal pressure to balance the hydrostatic head and keep the face dry long enough for the next ring sequence. In the most unstable zones, we resort to ground freezing. Liquid nitrogen circulates through pipes drilled around the alignment. Pore water turns to ice, and the entire mass stiffens into a temporary load-bearing barrier. Each intervention changes the material properties the machine encounters, rewriting the conditions the original surveys could not predict. We resume the drive only after sensors confirm the updated ground model matches the reality at the face. The experiment does not stop. It updates, and we design for the possibility that it updates badly. Every subsea tunnel of this scale carries a parallel service bore, a smaller tube running alongside the main drives from the outset. It supplies fresh air, removes exhaust, and carries power and drainage lines, so the primary headings never become sealed conduits. Above all, it functions as a permanent escape route. If a collapse, a fire, or a sudden inflow blocks one bore, crews can cross through frequent interconnecting passages and reach the surface without retracing their steps. The service tunnel also advances ahead of the main faces, returning continuous geological data that refines the model in real time. By accepting that risk cannot be eliminated, we embed redundancy into the geometry of the project itself. Then came the moment the model had been predicting for years. Deep beneath the seabed, the two boring machines one driven from each shore, finally reached each other. The alignment error, when measured, was less than a few centimeters across, kilometers of blind excavation. That number is not a footnote, it is the result of the experiment. It tells us precisely how much trust we can extend to subsurface geological models. Enough to build on, never enough to stop refining. The rock had shifted our predictions, subtly as it always does, but not beyond what the redundant systems could absorb. The lining had held against the pressures the calculations anticipated. The escape routes embedded in the geometry were never needed. Every loop we had opened in the preceding months closed at this junction, in the measured gap between what we expected and what the Earth returned. We did not conquer the geology. We negotiated with it, revised our terms in real time, and arrived, together, from opposite ends, at a result the ground itself ratified. What we built was not only a tunnel, it was a proof that engineering can operate inside irreducible uncertainty, not by eliminating it, but by designing systems that remain coherent as it shifts. Every sensor array installed, every lining segment revised, every geological model updated mid-drive. Those were not contingencies. They were the methodology. And methodology, unlike concrete, does not stay buried. The geological profiles we corrected now anchor the predictive models for every subsequent subsea proposal that cites this project. The boring machine telemetry we accumulated rewrote the sensor standards for soft ground marine drives. The revised lining tolerances became reference values in codes governing tunnels we have not yet begun to plan. This was not a construction project that happened to use science. It was a scientific experiment that happened to produce infrastructure. The ground was the laboratory. The schedule was the protocol. And what we carry forward is not only the passage beneath the water, it is the updated understanding of what it costs, in knowledge, to earn it. We have one question we cannot yet answer. If this tunnel, this one, with all its cost and consequence, was the first real calibration of these methods, then the next one changes everything. Not because the engineering is different, but because the engineers are. They carry the data now, and the proposals already exist. Tunnels longer than this, deeper than this, running beneath corridors of ocean we have not touched. The next project begins where this one ends, and the data we earned here is what makes it buildable.